Great. So as you can see, I am right now actually in my guest room. This is my first talk from my guest room because my husband's in the office and I have two puppies downstairs, but we'll make do. So today I'm going to talk to you about cloud architecture for the data scientists. This is going to be, it's great that I'm going after Robert and Jordan because it was a really good introduction. And I don't have to go through some of the things that I was going to talk about. But my talk is going to be a little bit scrappier, I think, and kind of bootstrapping together an environment for a data scientist in such a way that data scientists, I think, can work better with software engineers. And this is just my opinion in general. I'm going to go through the architecture in the context of a case study that goes through an astronomy case study, actually, because I'm an astronomer. I have a PhD in astronomy, because that's the best way, I think, to kind of get an idea of what I'm talking about. But first, let me tell you a little bit about myself and where I come from. I'm at High Alpha currently, which is a venture studio in Indianapolis. And a quick note about that, High Alpha Venture Studio is part studio, which conceives and launches and scales enterprise cloud companies, and then it's part traditional capital fund that invests in software companies as well. And we think this is a new model for entrepreneurship that unites the company creation with venture funding. And so it's really been fun to work at High Alpha for the past about a year and a half, and we've launched a number of companies, and I'm listing them here. And just to mention that a number of the companies that we work with have this sort of problem or issue of uniting data scientists and software engineers to put machine learning pipelines into production. So I think this is very relevant in a number of cases. And also just to mention, we work, our data science team works with external companies as well. So if you need help with things, I'm always willing to help. A little bit about myself. Like I said, I have a PhD in astronomy and I've worked on a number of astronomy projects. After I finished my PhD, I also worked on a number of other projects. I'm just going to mention them here because I think it's relevant for some context. I worked with NASA a little bit on some real-time streaming pipelines to do machine learning on satellite imagery. So they wanted to do classification on different types of land coverage and looking for water and that kind of thing. I also worked with NOAA to build their big data project, data distribution hub. And so that also had a real-time streaming component, getting weather in real time and having that distributed to data scientists who want to do machine learning on that. And then also I worked a bit with the GDC Genomic Data Commons data portal from the National Institute of Health, National Cancer Institute, and that also used a very similar platform and similar pipeline. And so if you're interested in this, this idea of cloud-based architecture for data scientists, and based on open source tools, we've written a paper called A Case for Data Commons Towards Data Science as a Service, and that was published in a special issue of Computing Journal. So let me get to it and talk a little bit about data science and a little bit about engineering and how I think there's kind of like a different mindset for both in terms of the language that people use and the tools people use and sort of their priorities in general. And I'm going to try and sort of build a bridge between those two, the data scientists and the engineers. And so actually I started, I'm not sure if I mentioned that, High Alpha as a data scientist, and I've kind of transitioned into the role of machine learning engineer because I like to build pipelines in general, and I think that kind of stuff is really interesting. So again, this is my opinion, but having worked on a number of these large-scale projects with both data scientists and software engineers, I have kind of a strong opinion about what the context is for these different groups. And so I'll just give you what I think is the wish list for data scientists, and being one myself, is that if I'm going to write a machine learning pipeline, I would really like to code in a familiar language. I use Python, a lot of people use R, and I want to be able to use that in my machine learning pipeline. I also want to be able to use familiar tools, and we saw Robert and Jordan introduce Jupyter and Jupyter notebooks, and that's something I definitely want to be able to use. I want to be able to customize my environment. Can I move this box? I can't see behind my face. No, I'll just read behind my face. Okay. I want to be able to customize my environment for my use case, and I want to be able to use the tools and the packages that I want to use. In Python, a number of people use scikit-learn or TensorFlow, and I want to be able to use really specific packages that I know will work with my code. I also want to be working in a development environment that looks like it will in production. Like I said, it's important to have those same packages that I'm working on when I'm developing. Those are going to be the ones in production so things don't break. I also want to be able to use my own laptop and run code locally because, you know, I work on my laptop all the time. I don't want to have to bother software engineers to spin me up some compute environments, and I want to be able to do that cheaply or free because I don't want to leave something running for a long time and run up a huge bill, which I've done before. So I wanted to be able to do it cheaply and free, so I'm going to talk about some open source tools here. I want to be able to iterate quickly without breaking things, which I can do on my laptop. I want to make sure my data is science quality in a lot of cases. That's more important in academia and in research, but I want to be able to make sure that my data is formatted in a way that I can really control. And then I want to be able to update my code as needed. So those are sort of the wish list, I think, for data scientists. So let's go to engineering. So that wish list is different, I would say. So I want to be able to use existing architecture. And I want to be able to integrate with my own system because I'm working, you know, on my system and I have some existing tools, and I really don't want to have special snowflake environments just for my data scientists. I want to be able to limit resource consumption because I don't want you, again, spinning up a bunch of stuff and taking over my environment and running up bills. I don't want to maintain another environment. I want to limit your access to the system. And I want to do things like minimize data volume just minimize all the impact of the data scientists and avoid data scientists in general, I would say, is on the engineering wish list. And I can say that because I'm a data scientist, so that's fine. I know I should be avoided. Okay, so the compromise, I would say, between the data scientists and the engineers is what I think works really well, and it has worked really well in a number of the projects that I've been involved with, which is a streaming framework with Dockerized analytics. And so you can see there is a great picture of a data scientist and engineer really, really happy with that compromise, and I'll tell you why. What you can do, I would say, with a streaming framework, and specifically I'm talking about messaging and message queues, which are available on all the cloud platforms and also in open source, is that you can have your regular environment that software engineers are maintaining, and you can just kind of send messages out to the data scientists who might be working on their laptops, running their own code. And then you can send messages back, and you can send either actual data, which I'll be talking about, or you could send some queues for the next part of your pipeline if you want to do ingesting and then aggregations and training and inference like Jordan and Robert were talking about. And if we want to be able to do this in a robust way, I advocate especially for Docker, for containing environments and for limiting resources. And that may be something that a data scientist has to kind of learn about, but hopefully in this talk, it'll give you an idea. If you're an engineer and you want to talk to a data scientist, here, nudge, nudge, you should kind of use these tools. And if you're a data scientist talking to an engineer, you might be like, hey, you know, if you want me to be able to not bother you anymore, let's kind of use these tools as well. And so a data scientist can, you know, run this kind of framework on their laptop using open source tools, and I'll talk about that. And then once you get things kind of hardened on your laptop, it's really great because I think this framework is really easily extensible to push all your code into production, and basically in its own kind of sandbox cloud environment where you can really get this running well. So the case study I'm going to talk about is streaming machine learning pipelines in astronomy. Like I said, I'm an astronomer and I worked on some large scale projects that I'm going to talk to you about. But first, to give you some context, hopefully this is interesting, if not useful. In astronomy, a lot of things have changed really basically into big data problems. And so we have this new way of observing the sky in what are called sky surveys. And so this is basically listening to the sky in all directions. So you're taking a telescope, and instead of the traditional technique that you might think of is pointing a telescope at a certain location, like I'm going to observe this galaxy or the star, what ends up happening is that you take these special telescopes and sweep across the sky back and forth. And the reason why you might do that is because you can stack up these images as you're sweeping back and forth and just collecting data all over to look for things that might be really faint. And then also what you can do is you basically build a template of the sky, and then the next night when you look, you can see changing objects, and those objects would be like supernova or gamma ray bursts or changing asteroids that are moving around and that kind of thing. So I'll quickly I'll slide over this, but I just want to quickly give a shout out to the Zwicky Transient facility and the LSST, which paid for my research scientist position for several years. So ZTF is kind of a cool telescope that's doing the sky survey at Palomar Observatory in California. It has a really large field of view, 235 times the area of the moon, so it can image the entire northern sky every 3 nights. And this is something that was built, dedicated to detecting transients, which those are the changing objects in the sky, like I mentioned. And this is a precursor to something larger, which is coming online in a couple of years, called the Large Synoptic Survey Telescope, which was actually just renamed to the Vera Rubin Observatory to honor Vera Rubin, who discovered dark matter. And it's backronymed to the Legacy Survey of Space and Time. So if you Google it, I think this doesn't exist anymore, but it does. So this is under construction for full operations in a couple of years. It's really huge. It's pretty cool. It's in northern Chile. And this is an artist rendering of it here. You can see with the small trucks, and there's a person down there. It will image the entire southern sky every few nights, and it will gather about 20 terabytes of raw data, image data, every night for about 10 years. So it's going to be a huge project, 60 petabytes of data at the survey end, and 15 petabytes is just going to be the catalog. So big SQL tables. And what's cool about this is all the data is public. The stream data, which I'm going to talk about, the transient data, and the code is open source. So it's really cool. It's a cool project for people to work on, and it was a really fun project for me to work on. So I'll just talk about transients for a second and how they're detected, because it's cool. So transients are detected by a method called image differencing, which very obviously is the difference between 2 images. And here is kind of what I'm talking about. So this is a template. Let's see if you can actually see the difference. This would be the new image that you take, the next day. There's a template again. There's a new image. So that's the difference, and that's the little transient that we're looking for. Yeah, there you go. So that's how you're detecting these transients. It's pretty straightforward. It's a little bit harder than I'm leading on here, but it's a really cool way to find these interesting objects in the sky. And you might think that, you have this idea of the sky being really static, but it's not. And so these sky surveys are detecting millions of these objects every night. As they're sweeping the sky, they take images every 45 seconds or so. And what you end up with for the ZTF telescope is you're getting 1 million transients detected per night. And once we detect these objects, what you want to be able to do is characterize all the different parameters like size and brightness and shape, location, color, all those kinds of things, so that you can basically take that data that you have and you can stream it out in real time to other scientists who are interested in studying that data, and other telescopes that might be robotic that are going to follow on in real time. And so some of these objects might be supernova or that kind of thing where there's really time sensitivity to it. So you have to be able to implement your algorithms that do the machine learning to be able to detect and classify these different objects in real time really, really quickly. And so this talk, I'm going to talk about how we get scientists basically to be able to implement those in a machine learning pipeline. And so these numbers are just to show you how large the ZTF and Large Synoptic Survey will be. So the nightly data that is just the stream data, which is just all those parameters, there's a lot of parameters in there about brightness and that kind of thing, location, is about 1.5 TB per night. So just that data, not even the images. So it's a lot of data. Okay. So I'm going to go through a couple of the different, what I think are the data scientist requests and the engineering requests and the tools that you could use that are the compromise here, depending on different needs in this use case. So if I'm a data scientist and I'm working on the ZTF or LSST, I want my data to be really science quality. So I want a high fidelity data format that's really robust. It's going to be able to, treat all the parameters with the appropriate, as floats or as integers or whatever we need. And if I'm an engineer, I'm going to say, this is too much data. Can you please minimize the volume and the throughput so that my life is easier in general? And so we looked at a number of different formats for this data. And you can imagine this could be actual data that has all the parameters, or it could just be messages, again, that says, go to the next step in my pipeline. But the data format that we looked at, well, first I'll say what the traditional format is in astronomy. When we didn't have these sky surveys, there still have been telescopes that do this kind of difference imaging and looking for transients. And what we used to use, and in some cases it is still used, is this traditional format, which is XML based. And so you can see here, these are the different types of parameter names and their different values. And, this is just not pleasant, I would say. It's really verbose. It's very redundant. It's very heavy. It's difficult because you can't really type the fields, which makes it difficult to, be unwrapping and parsing data into in what you would say is the quality that you need. And I would say this is meant more for human inspection. So the current telescopes that are the not survey telescopes, they will detect about one object per minute or so. And so actually you can listen to this stream. I can give people a way to see this, and you'll see new objects that pop up every minute, but this is really more for human inspection. So I can see it pop up in my terminal, and then I can write down, okay, I should point in this direction, and then there you go. One of the problems also with this is that in the use case that we have here for these two telescopes is that we don't want to just be sending out these parameters, but we also want to be including images. So there's a lot of requirements for these projects. You want to be able to basically cut out the image of just that transient object so that people can actually do analysis in real time on the actual image. So how am I going to include images in this data format? It's not going to be fun. And then also, because it's big and heavy, it's not going to really scale to the millions of objects 10 million objects in the case of the LSST per night. I don't want to be sending this data around for that much data. And so we looked at a number of formats, but really Apache Avro was the one that kind of won out. And so if you're not familiar, you know, Avro kind of falls on this scale between structured and unstructured, of where you could say on the unstructured side would be, you know, just CSVs and that kind of thing, and then you could say, you know, if you're semi-structured, that might be in XML and JSON, and then when you're really kind of more structured and what's more powerful, I would say, or is the side of Apache Avro, and then in different, basically, database kinds of formats. And so what's nice about this is that it's really compact as opposed to XML's verbosity. And so on the right here, I have basically what Avro looks like, or when you're serializing data into Avro, what you have is a schema which defines what your data is going to look like. In this case, I have some namespace just to name it, and then I have types. So this is a record, and the name is the user. And then I have different fields. So I'm going to have a name and a favorite number and a favorite color. And then I can say, okay, this is the type of field that is. This is a string, this is an int, or whatever it says under my face right there. And so the data below, you can see that's the data that I want to be shipping out. So my name is Ben, I have a favorite color that's red, and my favorite number changes all the time. And so I want to be able to basically wrap that data with this schema, and that's what you do with Apache Avro, and you can ship data like that. And so this is a binary format. So it's much more compact, and it minimizes the data volume, which is what the engineers like. And it's also easy to read, I would say, and easy to structure if you're a data scientist. To characterize things with this, basically, it's a JSON schema format. What's also nice is there's a couple of packages that are user-friendly in Python, which is what a lot of data scientists like to use to wrap up this data. And what's interesting also is that it has a really strictly enforced schema, but it allows for evolution, which is unlike Google's protobuf, if you are familiar with that. In that you can use any schema with the data as long as the data fits the format. So you can change your schema later on, and if your data still fits that format, you can change that schema, which is really cool. And it also allows for postage stamp cutout files. So those are the binary images that I'm talking about. So what you can basically do is you can have a schema for that stamp, and you can, I'm going to name that, this is my cutout. I can have a file name, which is just going to be my regular file name, and then my stamp data I can include as binary. So that's what it looks like there if you're writing things in JSON, in Python, which is, you know, very familiar for me as a data scientist. So that's kind of the data formatting side of things in my machine learning pipeline. Let's go to the next step, which I would say is probably most of my talk here is talking about the actual streaming framework. So on the data scientist side, what they want is really foolproof real-time data access. And so by foolproof, I mean that, you know, if my machine learning algorithm kind of messes up, I want to be able to go back, even in real-time data, and be able to replay a stream of data that's coming at me and kind of, you know, fix all my mistakes. And if I'm on the engineering side, I want to be able to give you data, but I don't really want you to be able to access most of my stuff. You know, I don't want you to be hitting my database because who knows what you're going to do with it. I want to kind of just send you data in a way that I can control what you're going to do. And so I'll go through this traditional method. This is also something that you can run if you want to listen to some of the telescopes that are taking data. This is a software called Comet, which is the special Snowflake software that was written just for listening to telescopes. It's an event-driven Python module. What's difficult about this is that you have to be connected to the telescope data distribution mechanism at all times. And so if you drop your connection, you're going to miss data. So that's not a good thing. It's also difficult to filter and apply my machine learning algorithms directly to the data as it comes in. It doesn't sync to any database. So you can basically, you can write things out to files, but that's really not that fun, I would say. And it's not scalable to the LSST scale. So we wanted to find another software that could be used for this. And so what we looked at was Apache Kafka, and this is what we decided on. And so Apache Kafka is, I think when they first came out, was kind of branded as a more of a messaging queue and a log platform, but now they're really kind of rethinking themselves as a data pipeline software, because it's been really good and it's been used for a lot of people that are doing data pipelines, distributed data pipelines. And so this is essentially a messaging queue at heart, though. And if you're thinking about the structure that I'm kind of putting together with these different components, you can basically search and replace your favorite messaging queue here. But this one's open source, so data scientists can use it without running up a huge bill. But again, you could put in Google PubSub, and you can put in AWS's messaging queue and Azure's and that kind of thing. It's really nice because this is very scalable. You can get many consumers, and you can even run consumer groups in parallel. And what we use Apache Kafka for is to distribute the data out to these community brokers that we call them, which are different folks in the astronomical community that are studying different types of objects, again, like supernova or the planetary people and the asteroid people. What's nice about Apache Kafka is also that it syncs directly to database, so that you can keep your archive in sync with all the data that you're streaming out to scientists. So you can make sure, scientists can go back and see a history, because we want to make sure this is science quality. We gotta have a record of our data that's exactly what is being sent out. It's also good because you can sort of rewind the stream if you're disconnected, so you don't have to be connected all the time. And there's a number of friendly Python packages that you can use with this. And I have so the LSST basically wrote wrappers around some of the packages that connect to Apache Kafka. And you can see here, you basically just import an alert producer on the side of the distribution component, which defines some topic that the consumers can listen to on the other side. And how we did it is we define a schema with each data packet, so that you can figure out, you can change that schema also if you're on the other side and say you want to drop a bunch of the data that you're not interested in. You can use that kind of schema too, as long as the data fits the schema. So that's really cool. And also this runs in Docker, and I love Docker. So it's really easy if you want to spin up a development environment yourself, if you're a data scientist and you want to do that. And there's a GitHub link there for people who are interested. I've actually put the whole pipeline into Docker containers, and there's a compose file and a Kubernetes implementation of that as well. It's all open source, so people can play with it if you want to. Okay, and let's move on to actually writing algorithms and writing the machine learning analytics. And so if you're a data scientist, I really want to be able to write algorithms right in my familiar environment, use the packages that I want to. I don't really want to learn a whole new software like Spark. And you can ask me later about why we kind of dropped Spark streaming. I think somebody else is giving talk about Spark, so sorry. But it didn't work out for us, and it works out for a number of people. But in this case, it didn't work for us. And on the engineering side, you want to be able to, again, limit the resource consumption in the special Snowflake environments. And that's why we use Docker. And in Docker, you can kind of gently get your data scientists to use Docker by leading them in with Jupyter notebooks. And that's something that we heard in the previous talk. So this is just an example of a Jupyter notebook, which is, again, an example of literate statistical programming. So you're mixing in both your code and comments, basically like a real notebook with code. And so what's fun about Jupyter Notebook is that it also runs in Docker. And Jupyter, in fact, keeps Docker stacks, keeps their own Docker images. And so you can go to Jupyter's GitHub and you can get these images. And then you can kind of herd your data scientists into, hey, why don't you use this Jupyter Notebook Docker file? And what's great about that is that instead of having this special Snowflake environments, you can have your data scientists just put all of their packages and the releases and this that they want, the specific ones that they want, into the Docker image. And so this is great. And this is what the LSSC and ZTF use to run their analytics. And so in our case, you know, because we're using Docker and we want familiar environments, we settled on, let's have all the data scientists just write their algorithms in Python. And so what you have here, I have some code of what these filters look like. We call them filters because you want to be able to, you know, whittle down the stream into just the objects that you're interested in. So in this case, I can write my filter. This is obviously a very simple one where I can say, I'm gonna get the alert if this is a high signal and it's of this brightness, then I'm gonna return true, which will end up writing to a new topic or a new stream in Kafka so that someone else along the pipeline can listen to it or can drop it all together. So you can see in this case in the pipeline, what ends up happening is that you have this huge stream of data and you can run these kind of filters in between. And then the next data scientist who's interested in your data can listen to a different stream and you kind of build that pipeline like that, which has been really great. And so now I just have some builds here that I forgot about. So there's your telescope running to Apache Kafka. Here are your filters. I want to look at these types of objects, write them back to a smaller stream, and then you can write those out to the data scientists and astronomers down the line. Okay, so let's put this all together. We built this thing that is running right now. It's called the ZTF Alert Distribution System, or ZADS. And I'll show that we wrote a paper about it, actually. So I'll just give you a walkthrough of what that looks like. So we have a telescope. It's going to send all of the data to this place called IPAC, which is a NASA center, and that does the data processing and figures out the image differencing and detection of the sources, archives to a database, and then you can enrich the data that you have with also new parameters from catalogs of what you know about an object. And so that's another thing that's pretty cool about when you're running through this pipeline. Say I am in the middle of the pipeline somewhere and I'm running my algorithm or my analytic with this filter, I can update the Avro package and I can add new data and then just change the schema for the next person, which is really cool. Let's see. So the way that we implement parts of the pipeline in using Kafka is that we have Kafka at different locations, and we run something called Mirror Maker, which is a tool that you can use with Kafka to basically replicate entire data hubs. And so Mirror Maker also runs in Docker and in an image that was put out by Confluent, who is the company that maintains a lot of Kafka right now. And so how we have it set up is we have one topic per night. So every night you can subscribe to a new topic because maybe your objects of interest are only in one area of the sky, right? Because the Earth is turning, so you can see different areas of the sky every night. And we have a 3-broker cluster at this university, the University of Washington, that also runs their Kafka in Docker images, Kafka and Zookeeper. And so from there, we can send all of the data into our database, which just ends up being an archive of Avro files. So Avro is not just the actual messaging format, it's a file format. So you can keep all of your Avro packets together, and you can make them really small because you can use one schema for basically a whole night's worth of data. And so we have individual consumers who are listening to the stream and writing to an Avro archive, which is open. So if people want links to play around with some real astronomy data, I'm happy to distribute that. And then at UW, we also have clusters that are running this open source code that we wrote that subscribes to each of the topics and then basically sends it out to different folks of interest who are running their own analytics and supplementing that data and adding to it, streaming out to the scientists there. We also run our own analytics service that basically allows folks to upload their own Dockerized filters and use that kind of like as a personal sandbox where you can run your own algorithms and you can run your own analytics there. And that's, again, it's kind of its own cloud with its own mirror maker using Docker as well. And so, using those Dockerized filters, that pops out some data, and you can do things like find accreting of stars and save us from asteroids. So this is a very important system. You should know about that. Right now, this system actually supports up to 1.2 million of these alerts per night. And there's about 75 gigabytes per night of the data that's in the archive. The pipeline runs end to end about 20 minutes from the image being taken to that being available to consumers. And most of that is actually doing the image differencing. And the actual packaging and the transferring is only 4 seconds. So that's cool. And there's a link there if people are interested in the public data. And so I've also written how to do this at scale, to the LSST scale, which I'll mention a couple of interesting stats about that. So this telescope has 189 CCDs that need to be processed in parallel because it's actually a lot of data. 4K by 4K, 3.2 billion pixels per image. So if you took a basketball court and you covered it with 4K TVs, that's one image. And so you got to do a lot of processing really fast. There's a lot of new algorithms that are being written to do this. And what we need to do is be able to package data and distribute it every 39. Actually, so the restriction is every 60 seconds. So you need to be able to get it 60 seconds after the data is taken to the end user. And so again, we also have this basically an alert hub where all the data is going in the centralized place where it's being backed up by an archive and it's being sent to these different community brokers that are large organizations, collaborations of different types of scientists. And then again, running our own analytics cluster, which is the filter submission service. And so what's being built out potentially, this is not coming online for a couple of years, is having this user interface that's basically sort of a Jupyter hub. And you can imagine instead of writing analytics in code, you could write Jupyter notebooks, for example, Dockerizing that and then submitting it to a cluster where those analytics are running and they're winnowing down the stream to what you want, sending it back to Kafka in smaller streams and having folks listen to those. So that's about it. I have some more information here, some links if you're interested. There's the paper that we wrote about this alert distribution system and about like scalability and some of the tests that we ran. This code that I talked about is all open source, so there's some links to the ZTF and the LSST repositories, which will give you some sample data if you're interested, and can let you mock up your own stream, and we wrote it again. So it's all Dockerized, and there are instructions there to run things with Docker Compose if you're familiar on a single node, or in Docker Swarm, which is actually how I did a lot of testing on AWS on their Docker for AWS system. And then there's also ways to run it in Kubernetes with all the YAMLs there. And if you're more interested, I also have some technical notes that I've written and some tutorials on my website. And then some contact information there at the bottom.